we ended our last Diels Alder lecture on kind of a cliffhanger on how the Diels Alder reaction would occur. So we set up the basics on what things changed, and we'll go through that real quickly here. And then we said, okay, when and how, and we want to design an experiment to account for this. So, as our first summary, as we should do with all reactions, we need to decide what things changed. Okay, if we look just at our overall picture, we broke some pi bonds, okay, and we made some sigma bonds and a new pi bond. Okay, there are other possibilities for how we could try and break this down. This is just going to be kind of your jump straight at it. This is going to be the one way that works. One of the things that we discussed in that last video is that would then be a lot of things happening, and that makes it very difficult to decide when those things happen. And you'll notice at the very bottom, we've already got summarized that there's really only two ways this can happen. And you'll notice in that list, I mentioned nothing of the pi bonds. And as we said in that last video, that's because a pi bond can be drawn with resonance in such a way where we do not see the pi bond anymore. Okay, so we can think about our pi bonds as really kind of temporary bonds. Yes, they're important, don't get me wrong, they are very, very important, and they are critical for this reaction to go, but they aren't really being broken or formed per se. We're just shifting where those electrons exist. Okay? The sigma bonds, on the other hand, are significantly different because those we can't move via resonance. Okay? So really, when we're looking at our reaction, we've only formed two sigma bonds. And in the sake of this video, I refer to these as sigma 1 and sigma 2. So when we decide on this when idea, okay, what our actual mechanism might be, that's when we have to think about, well, how can these two things happen? And just like in our substitution reactions, when we had two things happen, we could look at them happening either simultaneously or sequentially. Conveniently in the Diels Alder, there's really only two possibilities. We can make sigma 1, then sigma 2. It's the same as saying sigma 2, then sigma 1, because there's no difference between them. Or we could make them both simultaneously. And so the hope in our lab circumstance was that the experiment we ran would allow us to then decide this. Okay? For the sake of this video, we aren't going to look necessarily at our specific experiment, but we'll look at some kind of end results. So we went through and looked at how those mechanisms would play out. What are the natural repercussions of it? And if we look at our stepwise mechanism, there is the possibility, because we have a sigma bond that can freely rotate, okay, that would then change the orientation of A with regards to B, which then says these two structures are not equal. So we would end up with two products. If we go through and take a look at the what I call DA2, or our simultaneous mechanism, there is no way to interchange A and B, which then means I get only one product. So if we pick and set up our experiment appropriately, we can look at our products and say, do I only get one product or did I get more than one? If we get more than one, we're probably looking at the stepwise mechanism. If we only get one, we're probably looking at the simultaneous mechanism. The other thing that I suggested in that previous video is that you use some models and go through and actually try to physically move and organize these atoms in the process of making the new pi bonds. You'll notice that I don't have any pi bonds in this, and I'm representing those by these gray atoms or gray bonds aiming straight down. Okay? And then I left them open on the Dienophile. The intent is that really there is no good way to do this with any model kit, because our pi bonds, once they're made in a model kit, are pretty stagnant and we can't change them easily. So here we're using the representation of those gray atoms as our p orbitals, and those are going to be the places where we can form or break double bonds. So as we go through these, what you need to do is move the model kit and see how the atoms necessarily change and shift their orientations relative to each other. It's not an easy thing to go through and do, but it is an important thing to nail down. It'll help you minimize the need to memorize the end results in these reactions. So again, build the model kits, work through it with me as we discuss them. One more thing actually on that slide. Notice again, I'm always showing the Dienophile, which I'll call DP in this case, and the Diene, I'll call D. The Dienophile is always coming in from below the Diene, okay? And the Diene is always above. There is the other orientation. I just feel that this orientation is easier for me to draw, and it's also easier for me to see if I use the model kit that way as well. Okay, but again, it comes down to perspective. You got to find what works best for you. If you have questions, just talk to me and we'll work through a few examples with the model kits to help you see what's going on. So we can go into the lab, try and figure out what's going to happen between them. So here we've got two kind of experimental setups. So if we take a look at experiment 1, you'll notice that what we're starting with is a diene that is perfectly symmetric, and our dienophile is also symmetric. Okay, in both cases, in both experiment 1 and experiment 2. The one big difference is that we're looking at the cis dienophile as opposed to the trans dienophile. Okay, and we'll discuss why we did that in just a second. So if we go through and run experiment 1 with the cis, what we would expect is if we had Da1, we would have two products. Okay, where those two groups, okay, those two aldehydes have the potential of showing up either on the same side or opposite sides of the forming ring. If it was Da2, we'd only get one product where they'd have to be on the same side. Okay, and that's because they're locked into that same side orientation because of the double bond. So if that double bond is ever a single bond for any significant period of time, we get rotation. If it's not, then we would expect it to stay locked in. So we run the experiment and we end up noticing that we only end up with one product. The one product where we have the cis groups. Okay? Well, we started with cis and we ended with cis. What does that mean? One product. Okay? That suggests that the Da2, or the simultaneous mechanism, is the one that's favored. Okay? As a good scientist, we should go through and modify our experiment. Maybe the cis orientation is particularly stable and it's always going to form the cis. So that's why we try the experiment again with the trans, and we want to go through and test it again and see if maybe we end up with just the cis again. Okay? If we end up with anything other than the trans, our concerted mechanism seems to make sense. And we go through and look at our results. The end result is that we always ended up, is that we always ended up with the trans result. The conclusion of all of this is that the Diels Alder reaction is a concerted mechanism. It happens in one simultaneous step. We end up having the electrons from our diene attack the dienophile, which then causes electrons to shift out from the diene to form the new sigma bond, and we end up with our new pi bond. So we have our sigma 1 forming, our sigma 2, followed by the new pi bond. Okay? And this is going to hold true for every single one of our Diels Alder reactions that we'll ever see. Okay? So they're always combined, they're always in this concerted fashion. Everything has to happen at once. Okay? So this is kind of straightforward. We can look to the arrangement of our groups off the Dienophile. We look at our starting material and we say that arrangement must be the same as our product. Okay, so that's kind of nice and straightforward. We do still have to worry about enantiomers, okay, or the possibility of enantiomers. In the case of that first one, we shouldn't have to worry because we have an internal mirror plane, so there's no enantiomer. In the second reaction, we do have an issue with an enantiomer because if we look through there, there isn't a mirror plane, so we actually have a second product that is the enantiomer. This is not the second product that we're talking about in the Da1. Okay, that is a separate situation. Okay, and I know that's one of the things that makes the Diels Alder reaction tricky. What happens if we now look at the diene? What happens if we now add groups to it? How is that going to change the orientation? Well, if we look at these situations, or these two reactions here, we might go through, or we should be able to go through and predict the number one. We're going to end up with a cyclohexene. And you'll notice that I almost always consistently draw that new double bond, okay, on the side where the dienophile was. Okay, and that's just because that's easier for me to see and work with. Realize on a multiple choice exam, more than likely you'll see the structure rotated. It's not necessarily going to be in the exact same orientation. The next part, we have a cis dienophile, which then means when we draw out our product, we need to show those groups in the cis orientation. Okay? In this case, I'm going to show them both up. It doesn't really matter, both up or both down. Okay? But the new dilemma that we've added in here is that we have this extra methyl group. And if we've maintained our geometries here, we should be drawing it at this position. And we might be happy with that, except what you now need to focus on once you draw your product is that that position is a chiral atom, which then means we have stereochemistry. We need to specify that chirality. Okay? And that's where we then need to evaluate the dynamics of this reaction. Should that be wedged, or should that be a dashed bond? Okay? And that's trickier to see. Okay, what we have to think about is what is happening in the formation of the Diels Alder reaction. And this is where I'm actually going to have to take a step back because I have a hard time visualizing these. And I knew I drew these as wedged, but I'm actually going to switch those to being drawn as dashed. Because again, I have an easier time of seeing the reaction occurring if I'm showing my dienophile coming in from below. So as it comes up from the bottom, and as a gesture, I have to actually see this on my end. As it comes up from the bottom of the diene, okay, this bond, okay, is now kind of getting in the way. And what has to happen is this carbon now has to kind of adjust to an sp3 format. So this bond then must either rotate down, okay, and be the same direction as our new bond, or it needs to rotate up. Okay, and I've always had a hard time seeing this. Well, how can we tell? Well, I would make the argument that we shouldn't actually be looking at that bond. We need to be looking at this bond to the implied hydrogen. If our dienophile comes up from the bottom of the structure, where does that hydrogen need to go? If it rotates downwards, I know there's lots of arrows, but if it rotates down, it butts into this structure. So it can't possibly rotate down. That hydrogen, that interior hydrogen, must rotate up. Well, if it rotates up, what does our methyl then have to do? Oh, well, it'll have to rotate down. Well, if it rotates down, it is necessarily going to be dashed. Because of how I drew my dienophile, those two carbonyls, because I'm saying I'm looking at the bottom attack, will then also be as our dashed lines down. And now everything is on the same side. Okay? So let's switch it up. Okay, in fact, actually, I'm going to say take a moment. What I want you to go through and do is take a look at that next one and see if you can come up with the product before we walk through it. And I will walk through it here. So again, pause the video and take a swing at it. Okay, now that you've tried it, so again, our basic skeleton, okay, where I'm showing my diene, sorry, I always call them backwards, drawn in there is my basic blueprint. I then have my dienophile on the outside. If I take a look at my dienophile, it is cis, and because again I like showing the below orientation, Those are then going to be dashed going away. Okay, so I can get those drawn on. Now the question becomes is what do I do with the methyls? Okay, so we'll call it methyl 1 and methyl 2. I know for certain that they need to be attached to these carbons. But now the question is, where are they? Are they wedged or are they dashed? We should use the same logic we used in the previous case. Because I'm doing this Dienophile coming from the bottom orientation, what I want to do is look at the innards of my structure. That one methyl group cannot rotate down. If it rotates down, it butts immediately into the Dienophile, and that becomes a problem. So it must rotate up. Okay, well, since it's the one that I'm concerned about, if it rotates up, it's now aimed at me, it needs to become wedged. Okay, what about methyl 2? Okay, again, I have a hard time seeing the outer ones, so what I want to do is look at the inner ones. So I'm going to clean some of that up a little bit. The inner atom is an implied hydrogen. And again, because the Dienophile is coming in from the bottom orientation, okay, imagine these being stacked, this piece is on top. That hydrogen has to rotate up. It has to rotate up away from the approaching, let's write that down, away from the approaching Dienophile that's coming in from the bottom. Well, if it rotates up, then number 2 has to rotate down. Well, since I'm looking at this from the top, if it's rotating down, that must be dashed. And I've now got my orientations set up. Okay? Not easy to visualize and see. It takes practice. And not only does it take practice, it's a very common question to see on exams where the structure is then flipped or spun or rotated. Okay? So for instance, this one is often shown perhaps like this. And it's one that, again, I have a hard time with, so I might actually be drawing this wrong. But I'm going to try and do it right. I think I actually have it correct. That is a valid answer. Okay. We also have the potential for enantiomers in this case, so the enantiomer could be provided. And that would also be a valid answer for this. So we got a lot of stuff that we have to be careful of and we need to watch out for. So, again, what I've shown are the sigma down orientations. Remember, you do have the sigma up, okay? And the sigma up is going to pop up here in a lot of cases. The sigma up orientation, oh, I had to do a flip on it, didn't I? So give me a second here. For that first one, if we drew the sigma up without showing the fact that it's an enantiomer, okay, see the mirror image, okay? If we drew our sigma up orientation, there's our diene, there's our dienophile, and our sigma up orientation, when this comes in, these need to be wedged, and because that's coming in, this then comes up at you. Okay. Obvious? No, I don't think so. If you see it, great, phenomenal. Buco for you. I have a hard time seeing it. Okay, but that's kind of the orientation that's happening. Okay, you may not particularly like how I've got these drawn, but what I am trying to show is that we have the enantiomer forming in each of these. Okay, the enantiomer is a perfectly valid and equal structure. We have to watch out for that. If you have a hard time with this visualization, I'm fine with that. What you're then going to be left with is what I've got summarized below. What you would do is take your diene and your dienophile, and we can now see how those orientations translate into the up-down positions of your final product. Not easy to memorize, exceptionally challenging question. If it's something you just want to accept as a point loss, then by all means go ahead and do it. But this is what you are responsible for knowing and processing through. The next big question that comes into play, which was a question from the lab, from those of you paying attention, orientation effects on the Dienophile. You'll notice that when we drew out those previous reactions, okay, and I'm going to redraw them here real quickly, so give me a second. When we looked at those previous reactions, you'll notice that when I drew out the Dienophile, these substituents were always aimed towards the diene. You never saw them where the substituents were aimed away from the diene, okay, as in that other circumstance. And yet, if we go through and look at how I naturally drew this example reaction above, you'll notice that where did I draw the substituents on the Dienophile? I actually drew them facing away from the diene. Okay, and that's kind of an odd orientation. Well, the reason I drew that is it's easier for me to see and draw the connection between to get my final product of my cyclohexene. However, that orientation is actually not the correct orientation. Okay, and what do I mean by that? We have two possible orientations. One, where the diene and its substituents are aimed towards, the Dienophile and its substituents are aimed towards the diene. And then we also have a situation where the substituents are aimed away from the diene. Okay, this towards and away from system gets us the potential for two possible products. Okay, one is known as the Endo product because we have things coming inside. Okay, we have our substituents, quote unquote, inside the reaction, or our exo, where the substituents are outside the reaction. Okay, so two possible orientations, two possible products out of this. This kind of makes a big mess of all of my reactions. And yet again, if we go back to how I've been drawing things, I always show them on the inside. Well, why did I always show them on the inside? It turns out that when we run the Diels Alder reaction, we almost get there. Just a second, we'll come back to that. Your endo generates a sterically hindered product, okay, which is a bit challenging. Okay, we've got this big old group of electrons closer to a 2-carbon bridge as opposed to the 1-carbon bridge. That means I have more electron bulk in here. This is a steric hindrance issue. If we go through and look at the exo product, I'm taking that big, large group and I'm putting it near the 1-carbon bridge. This is less sterically hindered. So if we think back to how we should be evaluating our reactions, steric hindrance is a big, big aspect to it, and we try to minimize that steric hindrance. So we might think the exo product is the one that is favored. Okay? Interestingly enough, when we run the experiment, we only get the endo. Okay, well, what the heck's going on? If steric hindrance plays such an important role, why is it not being an issue here? Okay, well, the only reason the endo can become a more favored product has to do with something other than thermodynamics or energy. Okay, our sterics is looking at an energy argument. Okay, the endo product ends up being favored, and the only way it can be favored is because its transition state must be lower in energy than the exo product. Okay? Said another way, the exo or the endo product happens faster of a reaction than the thermodynamic product, which ends up in this case being slower. If we bring time into it, what we're saying is that this faster product is our kinetic product, because that has to do with time, and our exo product in this case is our thermodynamic product, because that's looking at energy. Okay? So we have to be able to balance between these. And the question might arise, well, why would I get the kinetic product when very commonly I see the thermodynamic product? And this has to do with that transition state. To get that kinetic product, the transition state energy is significantly lower, which then prevents the formation or minimizes the formation of the thermodynamic product, and I end up not seeing it. So if we try to draw this into an energy diagram, look at that, I switched my color codings on this. If we start with our reactants, well, our reactants are the same energy because they're the same materials. Okay? And it turns out that the Diels Alder reaction is exothermic, so our products are going to be lower in energy, period. So exo and endo, not exothermic, different thing. Okay? So let's take a look at the endo product, which I've got in red. The endo product, because of that steric hindrance, should be higher in energy than the exo product. Okay? This should be lower in energy. And if we just looked at this picture, we would predict that that exo product, this color coding is bothering me, that this exo product would be our favored product. And yet, somehow, we don't see it being favored. It's not the result. So something else has to be affecting this. And it's not the energy of the products. Okay? That something else has to do with the transition state. How do we transition between these? Well, what's happening is the transition state, sorry, it's a horrible drawing, for the exo product is significantly higher than that for the endo product. What does that mean? The activation barrier is so much lower that what I end up seeing is just the formation of the kinetic product. Okay? So this is kind of a neat little result here. And we'll end up seeing a lot of our reactions kind of bounce back and forth between kinetic and thermodynamic. Okay, so you're responsible for thinking about these issues and how they can manifest in the end results. So when it comes to Diels Alder, always, always, always run it as the endo reaction. You won't have a problem. You'll end up with the correct answer. Okay? Speeding the reaction. Okay, if we want to make the reaction go faster, we need to make our reagents more reactive. Well, the reason they were reactive is because of positives and negatives. Well, we have an issue with our Diels Alder reaction. Where's the positive? Where's the negative? Well, there isn't one. Okay? That's what our alkene does, is it neutralizes all of that charge. Okay? We don't even have an electronegative atom to help push it along. So what we've got to do is decide which of these is most likely to be the nucleophile, which of these is most likely to be an electrophile. So if we go back to our definitions, our nucleophile is supposed to be negative, and our electrophile is supposed to be positive. Well, if it is negative, it is going to be the source of electrons. Which of those two structures has more electrons? Okay. The diene has more electrons. It is more likely to be the nucleophile, and the dienophile is more likely to be the electrophile. Okay? So if I want to speed this reaction along, I want to somehow change or alter the structure of these so that the nucleophile has more electrons. Because the more electrons it has, the more likely it can be a nucleophile. And the electrophile, what I want to do is make sure it has less electrons, because then it becomes more and more positive. So this is where we can introduce the concept of what's known as an electron withdrawing group and an electron donating group. Not particularly important where we place them. So let's just put them at the end. We have an electron donating group, or EDG, D for donating. Or we could put on an electron withdrawing group with the W for withdrawing. Okay. The whole point here is to make the nucleophile or electrophile more reactive as a nucleophile or electrophile. Could we swap these two? Yes. And it would, in theory, speed the reaction, but we aren't going to see as drastic a speed to the reaction. Okay? So we just went through and explained all of that. Deciding whether it's electron donating or electron withdrawing. We'll keep coming back to this. but our electron donating groups have more electrons than a hydrogen atom. Hydrogen atoms are our 0 point. Anything with less electrons than a hydrogen atom is an electron withdrawing group. So a donating group, for example, could be an oxygen. Let's put on an ether. That oxygen has lone pair electrons. Those lone pair electrons could donate into the structure. If we push resonance around, what charge builds on that last carbon? Negative. There's our nucleophile. Okay. What if we put on, instead of an oxygen, we put on a carbon? Okay, and let's just make it a methyl. Well, carbon doesn't have an extra lone pair of electrons, so it's kind of in a weird gray area. Okay, this is where our definition, more electrons than a hydrogen atom. Well, a hydrogen atom, if I draw out its Lewis structure, has 1 electron. How many electrons does carbon have? More than hydrogen. What does that mean the carbon is? It is an electron donating group. Okay. As it shares electrons in, we start to build a larger negative on that terminal carbon. Okay. This is not a resonance argument at this point. Okay. We're just having electron sharing, okay, that kind of pushes density into the structure, making it more reactive. Okay. What if we switch this up and said maybe I put on a carbon, because carbon has more electrons than hydrogen, and I attach to that carbon an oxygen, because oxygen has more electrons. Okay, well, now the question was, shouldn't that still make that last carbon more negative? Well, the color coding might give you a hint. Okay, before we start looking at resonance within our diene, let's take a look at the resonance within the group we just drew. That pi bond is going to shift to the oxygen because oxygen is more electronegative than carbon, which then means, if we erase and draw our resonance structure, the oxygen becomes negative, and yes, that has more electrons, but it's not attached to our diene. The carbon becomes positive. What does that carbon do? Well, it'll find electrons from our diene. Those electrons come out to stabilize it. But then the next carbon needs electrons, so we can do more resonance, and the charge that ends up building on that last carbon, a positive. So the carbonyl group is actually electron withdrawing. So we have to look at resonance when we're looking at the less electrons, or electron withdrawing groups. So as a brief summary, we've got some examples of some electron donating groups. Notice that they all have more electrons than hydrogen. The big tip-off is that we have an atom with lone pair electrons immediately attached to our structure. In our electron withdrawing system, we have atoms that are missing electrons. Our carbon, as it's attached to our diene or dienophile, carries a partial positive due to the resonance with that oxygen. The nitrogen in our nitro group, which is an important structure to remember, okay, hugely important, because you'll see that all over the place, that nitrogen carries a formal positive charge, okay, which means it is super electron withdrawing, because it will always be positive. Okay. The carbon in our CF3 is also an electron withdrawing group, again, not due to resonance, but these fluorines are so electronegative that they're going to start to pull electron density away from the carbon, making that group overall as an electron withdrawing group. So if I'm going to speed the reaction, what I'm going to start to do is place electron donating groups on my diene, and I will place electron withdrawing groups on the dienophile. This can help me speed the reaction more so than if I had nothing on it. Last thing we'll address, what happens if we have symmetry, asymmetry in both the diene and the dienophile. Okay, so what I've drawn out here are your possible products. Okay, we could either have the diene or the Dienophile, because that's where I'm focusing on, show up where it is close to our nitrogen, or we could have it show up where it is really far away. Okay? Those two orientations are going to result in two different products. Okay? As we see over here, we've got a far away product and we have a close product. How do we decide which of those products, or both of those products, is valid? Well, number one, to decide are they both valid, are they different in energy? Well, close means I'm bringing electrons closer to each other. There's a steric argument here that might suggest that those would push away from each other. Okay? So sterics would suggest that the bottom one is our favored product. Okay, but is it? Before we use sterics, we must use an electronic effect. Okay? Where do the electrons want to go? Where do they, want is a bad word, but where are they most likely to be? Okay, to figure that out, what you need to be doing is looking at resonance. So if we start with our Dienophile, the resonance builds a positive charge on that carbon, okay, which will be the same case in both orientations. The nitrogen, due to its resonance, will build a negative charge on that bottom carbon. I want that negative to hook up with the positive. Which of these two orientations puts the positive closest to that negative? It's the top orientation, which means I end up with that as my product. Okay? If we use the electronic effect, that is going to be the one that's going to stump our steric effect or trump our steric effect and force that product to come out in the long run. Okay? So when you're looking at an asymmetry in both the diene and the dienophile, look to resonance to help you predict where things belong. Okay? And that's really our pre-reaction transition, if you will. Our big conclusion has everything on it. Okay? We've got our diene, which typically acts as our nucleophile. Our dienophile is our electrophile. We end up with a six-membered ring with the double bond inside it. There are variations off of this. For instance, if instead of reacting an alkene as my dienophile, I reacted an alkyne, I react one of those pi bonds away, I keep the other one. Okay? So we have to recognize the pattern. We can change the structure around a little bit, but the pattern still holds. Stereochemical relationships, there I showed only the down, the sigma down formation, just because, again, I find it easier to deal with, which will get us our stereochemistry. The regiochemistry is going to be defined by resonance, so you need to draw your resonance structures to help you decide how those pieces connect and interact with each other. And with that, in under 50 minutes, we have the end of this show. So thanks for watching.